Hello 151. I'll be continuing the discussion on Newton Raphson. So from last time I introduced how do we go from our Gauss-Seidel power equations into our fundamental equations on Newton Raphson. Basically, the one na dinerive natin before on my previous video, this equation for power injection and this equation for reactive power injection, those two will be our fundamental building equations for Newton Raphson. So gagamitin natin siya. Okay. Sorry, nagkaroon ng cut. Anyways, okay. So let's go back to the solution. Where am I? Dito. So I ended up with these power equations, this P and Q. So let's proceed to Newton Raphson. Yeah. So basically ito 'yon. Dito ako nag-end. Okay? So if we solve for these equations, just like nung ginawa natin with Newton Raphson before, if you solve for this equation of power and equate it to the injected power, this is basically the power in the lines going into the system, and this is the power from your generator and your load injected into the system from the generator and the load. If you solve for that equation, you'll end up with this. As you can see, they are not really equal. So what happens here is that this P injected on bus 2, which is negative 0.3, the reason for the negative is because it's from a load. So technically it's not being injected, but it's being drawn. So you are drawing 0.3 per unit power from bus 2, and then that is equated to these powers that is going into the system through the lines, which is equal to 0. So they are not actually equal. You have this difference of power here. Also, if you solve for the Q and Q here, they are also not equal. So again, Q injected is equal to negative 0.04, and that is equated to negative 0.05, which are again not equal. So you have this discrepancy again. So this is basically the scheduled power at the bus. So the idea is that on bus 2 is a PQ bus, so you want to have that much P and that much Q. You want to have that 0.3 and 0. This is not 0.04, this is 0.4. Sorry, this is not 0.04. I think I have to. This is not 0.04, this is not 0.04. This is negative 0.4. This is negative 0.4. Okay? Anyways, you want to have 0.3 and 0.4 on bus 2. So that's basically the schedule of bus 2. And then these computed values, these are your calculated power. So the power mismatch, we can define the power mismatch as the difference of the schedule and the calculated, such that you have the power mismatch equal to S scheduled minus S calculated. In which case you can get the power mismatch P2 as you can get the power mismatch P2 as negative 0.3 and the power mismatch Q2 as negative 0.35. Again, this is negative 0.4, not 0.04. So you have the power mismatch on P and Q. Okay, so looking at the equation of P and Q, looking at this equation and this equation, okay, so this one, your P and Q, I think I was able to mention this in Gauss-Seidel. Your P and Q is a function of voltage magnitude, voltage angle, admittance magnitude, and admittance angle. But take note that your admittance magnitude and admittance angle are constants because they are defined by your network, this one. Now this V and delta, take note that those are variables because those are just assumed values. We are actually solving for them. So you have P and Q as a function of delta V and delta as a function of voltage magnitude and voltage angle, such that this power mismatch can be defined as the power mismatch due to the change in voltage magnitude and the mismatch due to the change in voltage angle, or the difference in voltage angle. So I same is for delta Q. I think this yeah, oops, sorry, ang dami ko palang kailangan i-correct dito. So this is delta Q and this is delta Q. Okay, so yeah, okay, so I think these equations will look familiar to you considering tapos na kayo ng ES21. These are basically your differential equations. In matrix form, you can rewrite this in matrix form as this one, where you have this matrix of rate of change of P with change in voltage magnitude, change in voltage angle, rate of change of Q, delta Q over delta V. And from your linear algebra, you know that these are partial derivatives, which can be further represented as this one. So you have a matrix of partial derivatives multiplied to the difference of voltage magnitude and difference of voltage angle. Okay, so on delta P, currently we have delta P2 and delta Q2. Delta P and delta Q, on the change in P and change in Q, we have delta P2 and delta Q2. On change in voltage and change in angle, we don't have a change in voltage magnitude of bus 1 because that's the slack bus. We have a change in voltage magnitude of bus 2 because that's a PQ bus, so you are not maintaining any value for voltage. However, we don't have a change in voltage magnitude on bus 3 because bus 3 is a PV bus, and for a PV bus we maintain a constant voltage magnitude, so you don't have this delta V3. You don't have a delta V3 on bus 3. Yeah, a delta V magnitude on bus 3. So on delta V magnitude, you only have a delta V2. Okay? Wait lang ah. Okay, how about on the delta angle? So on the delta angle, you don't have a delta angle on bus 1 because bus 1 is the slack bus. It's the reference, so you maintain it as 1 angle 0. So it's always 1 angle 0 for every iteration. So you don't have a delta angle on bus 1. However, on bus 2 and bus 3, on bus 2 it's a PQ bus. So since you are not maintaining any voltage parameter on that, since it's a PQ bus, so you have a delta angle on bus 2. On bus 3, take note, even though that it is a PV bus, what you are trying to maintain on that PV bus is the voltage magnitude. So though you don't have a delta voltage magnitude on bus 3, you have a delta voltage angle on bus 3, hence delta voltage angle. So on delta P and delta Q, you have a delta P2 and a delta Q2. On delta V, basically on this matrix, you have a delta P2 and delta Q2. On this matrix, you have a delta V2, delta 2, and delta 3. Okay. Well, we're not done yet. Let's proceed to bus 3. So the equation for bus 3 is the same. Well, it's not the same as the equation for bus 2, but it's the process of getting this. The process of getting this formula is the same as on bus 2. So if you look at the power mismatch is basically the change in the difference of the schedule versus the calculated. These are the schedules These are the calculated values. Now, take note that we are considering bus 3 as a PV bus. Therefore, we are not maintaining a certain value of Q. So, we don't really mind the schedule Q on bus 3. We don't really mind whatever is the value on bus 3 because since, we want to maintain a certain P and a certain V magnitude. And that is that leaves Q as your variable. So we don't assume a value of we don't assume a schedule for Q. Because we don't assume a schedule for Q, therefore we're only concerned for now we're only concerned with delta P. We are not concerned with delta Q because we don't mind any schedule. We don't consider any schedule for Q. So for this for now we'll just consider delta P. So we want a schedule of negative 0.2. Our calculated value is 0, so your delta P3 is negative 0.2. So on delta P and delta Q you only have delta P3, delta P for PV buses. So we're done with all of the buses. We have bus 2 and bus 3. On bus 1, we're not gonna compute for that because it's the slack bus. It's always 1 angle 0. We're not computing for anything. Okay. So on the full matrix of delta P's and delta Q's, you have delta P2 and delta P3 on delta P's and delta Q2 on delta Q's. On the matrix of delta V and delta angle, you have delta magnitude of V for the magnitudes of the voltages because you don't have a delta for magnitude of voltage on bus 1 and magnitude of voltage on bus 3. And then you have a delta angle of 2 and delta angle of 3 on delta angles because you don't have a delta angle on bus 1. It's the slack bus. Okay. Now you have this full equation of partial derivatives. Basically, you have a P2 partial derivative of P2 on voltage magnitude 2, voltage angle 2, and voltage angle 3. The order of this is basically the same order as this one. That is very, very important. The reason why, it's basically matrix operations. Yeah. Okay. So for P3, it's dependent on the change in V2, delta 2, and delta 3. On Q2, V2, delta 2, delta 3. Same order as this one. Okay. So this whole partial derivatives matrix is called your Jacobian matrix. It's basically in this form: delta P's and delta V's. This is J1. Delta P's and delta deltas, J2. Delta Q and delta V's, J3. Delta Q and delta deltas, J4. So that's basically your Jacobian matrix. And then this matrix of delta P's and delta Q's, that is your power mismatch. Okay, so what we're gonna do is we're solving for the Jacobian matrix for each element here. We have 9 elements of the Jacobian matrix: 1, 2, 3, 3 by 3, so it's a 9 element matrix. I guess what's tricky here is getting the partial derivatives, because what we're gonna do with the partial derivatives is we're gonna go back to this equation here. This is basically the equation of P, and this equation here is the equation of Q, and then get the partial derivatives. For example, you want the partial derivative of P with respect sa ating magnitude V2. So it's basically the partial derivative of this with respect to V2. So I am assuming that you know how to perform derivatives. So the derivative of this would be V1 Y21 cosine plus, take note, V2 times V2 is V2 squared. So if you get the partial derivative of that with respect to V2, it's 2V2. So you don't cancel out V2. So it's 2V2, and then on the third term, it's V3 Y23 cosine. Or, yeah, this one. Okay, and then take note, I want to emphasize this one. This is a very very common mistake. I'm guilty of doing this most of the time. It's cosine of 0 delta 1, angle 1, which is 0, angle 2, take note, minus angle 2, that's 0, plus this is the angle of the admittance matrix, pi over 2. It's in rods, take note, it's in rods and not in degrees. Okay, that is very very important. I'll show you later why, but take note, for Newton Raphson, always use rods. Okay, so that's delta P2 over delta 2, partial derivative of P2 over with respect to the magnitude of V2, so that's basically 0. Okay, then partial derivative of P2 with respect to with respect to angle 2. So angle 2 is present in all of this. It's negative, so derivative of cosine, it's negative sign, but it's negative delta 2, so it's positive sign. So yeah. Okay, and then you perform that operation. It's basically this equation. The partial derivative of that is 10.05, and then partial derivative of 2 with respect to 3, angle 3. So it's basically just this term, this last term here. Okay, so its derivative of cosine is negative sign, so yeah, hence the negative. Okay, so it's negative 5.05. You perform that with P3 and with Q2, and then you get this final form. So this is your delta P's, this is delta P2, delta P3, delta Q2, and then this is a partial derivative of P2 with respect to V2 magnitude, with respect to angle 2, and with respect to angle 3. This is partial derivative of P3 with respect to V2 magnitude, angle 2, angle 3. This is partial derivative of Q2 with respect to V2 magnitude, and then angle 2, angle 3. Okay, so what do we get from this form? As you can see, you now have values for delta P and delta Q and the Jacobian matrix. So we can actually solve for the delta V's. And what's interesting here is that basically the delta V's is the change, is the difference of the voltage that causes this difference in power. Okay, so the idea is, if I get delta V using this equation, it's basically the inverse of the Jacobian times the matrix, the power mismatch matrix. If you get that you get this value for delta V's, and this is for delta V2, delta angle 2, and delta angle 3. Okay, and that's essentially the difference on the first iteration versus the second iteration. The expanded form for that, okay, so therefore you can get the value for the first iteration by getting this plus the previous iteration, which is essentially this equation right here. So the voltage on bus 2 magnitude will be your on iteration 1 will be the bus 2 magnitude on iteration 0 plus the change delta V2. The angle 2 on first iteration will be angle 2 on the 0th iteration plus the change in angle 2, and angle 3 is the angle 3 on 0th iteration plus angle 3 delta change in angle 3. Okay, so you get those changes. This is basically the reason why this delta is always in the rods, because you can only perform this operation if your angle are in rods. You can only you cannot perform this if your angle is in degrees. So you always perform this. You can only perform this if your angle is in rods. That's why it's really important that you take note that those angles are in rads. Okay, so doing this operation, then we can define our voltages for the first iteration, which is 1 angle 0, and then for V1 it's the slack bus, so it's 1 angle 0 rads. For V2 it's 0.9648 because of this one angle negative 0.0532 rads. And then for V3 it's 1.01, again because this is a PV bus and you want to maintain the voltage on that bus as 1.01, angle negative 0.0464, this one, rads. Okay, and then you compute for the delta P's and the delta Q's here, and then see if this delta P's and this delta Q's are within a certain tolerance level. So yeah, that's basically it. I guess if we continue to do this solution using an error of 0.000001, 5 zeros before 1 after the decimal place, we'll end up with 4 iterations with this voltage magnitude, with this voltage values for V1, V2, and V3. And what's, I guess, I don't know, interesting here is that with this much error, the result of the Newton Raphson is almost the same as the result of the Gauss-Seidel. The difference is that for Gauss-Seidel you'll reach this solution after 8 iterations. For Newton Raphson, you'll reach this solution after 4 iterations. Okay, so main takeaways for Newton Raphson versus Gauss-Seidel. Gauss-Seidel is a lot easier than Newton Raphson, but Newton Raphson reaches the solution very a lot faster than Gauss-Seidel. You're done with the iterations. You're done with the solution after 4 iterations versus after 8 iterations. You have a lot. The complexity of Newton Raphson is a lot higher than Gauss-Seidel because of the partial derivatives, but you'll still end up with basically the same answer, the same voltages. Okay, so and one more thing, by convention, on Newton Raphson you compare the delta P's and the delta Q's on the tolerance, whereas on Gauss-Seidel you compare the voltage mismatch on the tolerance. So it's power mismatch it's usually power mismatch for Newton Raphson, voltage mismatch for Gauss-Seidel. But well, you can still do voltage mismatch on Newton Raphson, but it's not very common. Okay, so I think that's it for Newton Raphson and Gauss-Seidel. Yeah, okay.